All right, so this review sheet, and I'm going to give it to whoever wasn't here tonight, tomorrow. So when I pass them out tomorrow, please remind me that you guys got a sheet so I don't wind up giving out multiples. Because, well, this thing's 18 pages long and it took 13 minutes to run on the copier, and I don't feel like sitting by the copier for another 13 minutes. But this sheet has everything you ever needed to know and more out of AP Physics B. So it's got some stuff on there that we didn't actually learn because I found this that another teacher put together, and frankly, this one is so good, I'm not nearly motivated enough to make another copy of my own. This sheet is fantastic. This is everything. If you know everything on this sheet, you will ace the test. I guarantee it. It's got the equations, it's got diagrams, it has explanations. Now, there is some stuff we didn't talk about. For example, in fluid dynamics, we never talked about the Magnus effect or Torricelli's law or stuff like that. That's fine. If it's something you've never even heard of before and you don't know it, that's perfectly okay. Not a big deal. But the more you do know, the better. We got frequencies in here. There's Doppler effect. There's even the math for the Doppler effect in here, although you don't need that. Optics, color, pretty much everything. So everything we've covered with the exception of quantum, that's on here. We just haven't finished it yet. Okay? So pretty much absolutely everything you should need is in this packet somewhere. Thursday, I'm giving you guys a copy of the learning objectives, the full 22 pages of learning objectives from AP Physics. And your assignment this weekend is going to be to go through and start marking which ones you don't understand. And next week when we get into review, we're going to sit there one by one. Okay, let's hear the ones you don't get, you don't know what they are, and we're going to go through and we're going to talk about each and every single standard. Because if you know how to do each standard on there, that's what the test is. If it's not on those learning objectives, it is not on the test. So if you ever have to ask, what should I be studying or what do I need to know? Bam, and the learning objectives. That's where you go. Learning objectives first, because that's official. This is something a teacher put together. Learning objectives are put out by a college board. Okay, any questions on that? All right, so I said I wanted to start off briefly just talking about the test. So don't forget the format of it. It is 2 parts, multiple choice, 70 questions, 90 minutes. You got about a minute and 10 to 18 seconds per question, something like that. So you don't have a whole lot of time. So the same advice that I would give juniors for the ACT is the same advice you should be following for the AP. If you see a question that you know is going to take you forever, skip that sucker and move on. Come back. But it's all about getting as many points as humanly possible. You are not going to get 100% on this test. You are not going to get 90% on this test. You are not going to get 80% on this test. I can pretty much guarantee if you get a 60% on this test, it's because you are freaking brilliant, okay? This test is a hard one. You are not supposed to get everything. So we'll go over all this again just before the test, but don't forget, answer the easy stuff first. Get the free points. Then tackle the hard crap. Don't ever run your friend. Run your bear. Crap. Back that. I switched that around. By analogy. No. All right. Point being, you guys get it. Free response, same deal, 90 questions. It's usually in the neighborhood of about 80 points or so. Sorry, 90 minutes, and it's about 80 questions.
90 questions.
That would be the worst test of all time. 90 free response questions. You have a week. Go. Oh, God, that would be terrible. All right. Any questions on the basic format? Yeah.
Do you penalize for guessing?
No. That got eliminated from, I think, all AP tests 4 years ago, 3 years ago? Yeah, that's relatively recent, but, I mean, they still have the quarter point penalty when I started teaching AP, but yeah, that's been gone for a couple years now, so you're good. So yeah, guessing doesn't hurt to just bubble random crap in.
Is he supposed to be dancing?
It's a play on Leonardo da Vinci's Venezuelan Man.
Yeah, but his arms are even at the spots.
What I like is this is what you're concerned about. This is your concern. Screw reviewing AP. No, I'm worried about that damn badger. All right. So, anyway. All right, so any questions on test format, stuff like that? All right, so I wanted to show you just a couple of quick study resources, things to look at, and then we're going to get into modern and radiation. Like I said, today should be a relatively short session. I don't see us going the full 2 hours. So we're just going to go over some learning resources. I'm going to kind of do a quick review of everything about atomic physics and all that kind of stuff. And then I've got 4 pages, 3 of multiple choice, 3 of free response. We'll pick some questions, we'll go over them, kind of crank through the answers. I'll give you some time to work on some, we'll do some together. Normally I would have given you these ahead of time, but I forgot. That'll happen in the future. But this one's kind of an ease into review sessions. And then the next set of review sessions, we start cranking out all of, like the next review session is all of mechanics in 2 hours. So we hit the ground running with that. We might, if we have some time left over and you guys don't want to leave, we might crank out a little bit of mechanics here today. We'll see. Huh? The next study session? I don't know. I got to think about it. I'll let you guys know by tomorrow. Do you guys have any preference when next week the next study session is?
Not, I guess it's too late to say not Monday, because like.
Not Thursday.
Was it too late to say not Monday? Who cares?
Okay,
Not
not
Thursday.
Monday.
Okay. Like, I don't know what you guys have going on in your lives, so.
Not Thursday.
I just don't want to do it on the days we have off. But that makes us not pretty good.
We have days off.
Yeah, Wednesday, Thursday if you're a senior. Because Wednesday, Thursday next week are ACT.
Yeah, that's like a good day.
Yeah, maybe we could do Tuesday. You guys, since you guys are the ones here, are you cool Tuesday or no?
No, there's like.
Wait, what?
Tuesday.
You've got a push on Tuesday?
But that's like right after school.
Tuesday's gonna be a party day.
Unless you're doing it after 8 p.m., I won't be able to do it on Tuesday.
Unless you're doing after when?
After 8.
We should not do.
I can't do it.
You would come to a study session after 8 p.m.
No,
Let's do
I don't have time
Wednesday.
until after.
Okay, well,
Yeah, Wednesday.
we'll talk. We'll talk. It's fine.
What day is the test?
What day is the test? Let's see.
Or like
So the prom is the 3rd.
I think it's the second.
So that means 4th, 5th, it would be the 12th. Yeah.
7th is Calvin.
But this one just sucks for me.
12th.
Is it it's the afternoon, right?
Morning. Oh, yeah. It's 12:30 test. Okay? All right. Hey, guys.
Shut up.
Focus time.
You don't say that anymore. Is it because we caught on to it?
Say what?
Shut up.
No, I have my phrases, but right now it's focus. Like I go through cycles. It's like anything. I'm a strange man, I'm a mystery wrapped up in a conundrum, wrapped up in around a gumball center. It's fine. All right.
In a quesadilla of.
Awesomeness.
Yeah,
All
there
right.
you go.
So the first website that if you're looking for a resource to go should be easy to remember. I told you about it at the beginning of the year, but I'll tell you about it now again. LearnAPPhysics.com. Honestly, if you cannot remember that website, I wouldn't bother using it.
We couldn't use it if we didn't remember.
You know what I meant. All right, LearnAPPhysics.com. At some point, the school's internet will decide to load. Okay. Someone want to go run out and pull the brush I got in the door?
Welcome.
I want to leave that propped open all night. All right, here we go. So this site is great for both B and C. So for you guys, you only particularly care about B. But for example, we are talking today about nuclear. So if we go to Physics B, we would just go down here to the topic we want, which is going to be in modern physics. Okay, so what they've got here, thank you, appreciate it. Whew, that was cold. All right, so what we've got here, let me close this thing out really quick. What we got here is they've got a whole bunch of videos. So videos from a variety of places, MIT, stuff like that, that will provide explanations of certain topics. For modern in particular, you're not going to want to worry about a lot of these, but stuff like mass energy equivalence, let's say you're running into problems, go to it. It's at least a video explanation. I personally think they're a lot better than something like Khan Academy because they've got the animations and stuff like that. It's not just someone sitting writing stuff down on a board, which is great, except you already learned that one way from me. So the animations and the other representations of the concepts can be a little bit helpful. On top of it, if you continue to scroll down the page, they've got a bunch, right here they've only got 3, generally they've got more. Example like AP AP questions, stuff like that. So it's another source. They're not true AP questions, but they're written in the same style as AP. So there's always the AP Central, things like that. This is another resource, so I highly recommend this one. On top of this, the other one, these last two are just for concepts. They're not specifically that great for example problems or stuff like that. But if you're having trouble with any of the basics, the first one would be the physicsclassroom.com.
I thought the Pirate Bay was the first one.
Nope, you saw nothing. You saw absolutely nothing. I don't know what that is. Really? You're blocking physics classroom?
Maybe they confused it with Pirate.
It doesn't even use
The physics classroom, not Pirate Bay.
No, seriously, I mean not the Pirate Bay. I don't even know what that is. I think my cat went there once. Shut up. Do as I say, not as I do. I don't know what this means. All right. No, I asked the
That's the link.
yeah.
I was wondering where it was. I'm going to spend the rest of the study session throwing things at you.
Go for it. Yeah, unfortunately.
Browse torrents, recent torrents, and literally every.
What? What is? Oh, I'm sorry. That's why I got blocked. It's not thephysicsclassroom.com. It's just the address for thephysicsclassroom.com is physicsclassroom.com.
Wow.
That the threw me off.
I'm worried about why it would be blocked. Just
Because a lot of places will go to popular sites like this one and put websites that have spyware and stuff like that on popular mistypes. For example, adding the word the. So that was probably why. All right. If you go here, they do have some worksheets if you go to this curriculum corner, but mostly what's going to be helpful for you guys is the tutorials. This is going to be mostly useful for things like mechanics and E&M, sound and waves a little bit. It's not going to help you too much with things like atomic or quantum or electromagnetic induction to a large degree. But a lot of the basic class concepts, they're just really good tutorials, really good explanations. So let's say you need to review vectors. So like I said, it goes through a whole bunch. You got a table of contents. It's got pictures. It's got good explanations. All this kind of fun stuff. It's got problems. It's got, not only does it have problems, it's got explanations of the answers. So it's a nice another resource for you to go to take a look at.
That's my father.
I don't care. Be your booty call. I don't give a crap.
What are you saying?
Might have said it could have been his booty call. I don't care. So again, it's got right. Anyway, so lots of explanations, lots of good stuff with this. Last one. This is purely for hey, I don't recognize what this word is. I want to see what it is. Is hyperphysics.
What?
I don't care what you do. Just the rule is if you drop the cookie, you eat the cookie.
That's the opposition problem.
Huh?
I didn't drop it.
Okay, I'm just saying. We don't waste cookies in here. All right, so like I said, last one is hyperphysics. You guys are way too young to have made hypercards before. Back when I was in high school, hypercards were the thing. What? Hypercards are like you make a card and then you add a button and that card links to something else. And so it's like making mind maps in index card form. It's interesting. But if you want just a quick overview of here's concepts that maybe I should understand, a lot of this stuff is well kind of above where you need to be. But for example, if you go, hey, quantum physics, what should I know? If you click there, here's a bunch of quick explanations. So like today we talked about the Planck hypothesis. So Planck hypothesis, which is apparently related to the failures of classical physics and is somehow tied into wave-particle duality. But let's click on the Planck hypothesis and just get a quick review of what it is. And so it's just a quick explanation, example calculations, and then it's basically a poor man's Wikipedia page of, hey, if you want this, maybe you should also take a look at these other options. So it's outdated. It's a style you're probably not familiar with. Like I said, this was phasing out when I was in high school. But it's a nice little quick overview of the big picture. Okay? Any questions on all those? Any of those?
They had the internet when you were in high school?
A decade ago, yeah, the internet existed. Back then, I may have had AOL, yes. It's okay, don't forget, I used the internet before the internet existed.
Dial-up modem.
Good money to make emails.
His dad worked at Area 51.
Dad did not work at Area 51. He visited Las Vegas from time to time. All right. So, questions on any of that? All right. Atomic physics. Let's talk. Let's rap.
Rap, do it.
No. Never. I'm sure you remember it and you don't want to hear me. I am the whitest of white men when it comes to rapping. All right. So,
What about Eminem?
got the sideways hat, got the chain.
What about Iggy? What about...
No? Okay.
Don't ever make that. Please
So, remember, good, the new game of these study sessions has become Make Jonah Cry. All right.
I like this game.
don't even start.
You don't have to shotgun stuff again.
You make yourself
No money, no water, no electricity, no
Electricity.
anything else.
No
electricity. Nothing that will kill you. Which is like,
So, we shouldn't have oxygen in here because oxygen will kill you.
well, not like excessive.
Fancy.
Excessive amounts of oxygen.
Actually, any oxygen will kill you. It's what causes you to age.
Remember
All
what
right.
about this French
Well, I'm dying anyway.
It's great one day.
Well, yes, I know oxygen allows you to age, but still.
I don't know.
All right. So, atomic physics.
Oh no. Oh, read the paper. It was just mayonnaise.
What a tragedy. That's the downside of running these late. Everyone's slap happy at this point, including me. That's the only equation you have to be able to remember for this particular topic.
E equals MC squared.
Get that
Get that
camera
camera
out
out of my
face.
face. I'll take this candle.
Okay, guys, again, I have to stress that not drinking is preferable when leading up to these study sessions. Because that's kind of something I got to report.
So
Where's that even from?
It's from the internet.
Then I don't want to know. The internet's a terrible place.
Like YouTube, like news reporter makes a baby cry or something like that. You'll find it.
Yes. All right, E equals MC squared. We're going to use this for something called mass defect. Okay? And we're going to run through an example problem of that here in a little bit. All right. Short of this, the only other stuff we've got to talk about, the only other things you should remember is the types of decay. Okay, so don't forget, we have we have a way of writing, I believe it's Z and A, a way of writing atomic symbols. I think that's Z and N, whatever. Point is, we've got the atomic symbol. Is that us backwards? No? It seems backwards to me for some reason. That's weird. Like I said, everyone's slap happy, including me. All right. So we have the atomic symbol, you have the atomic number, and you have the atomic mass. Okay? So, someone throw out an element. What's their favorite element?
Radon.
Radon?
Unobtainium.
Bromine.
Let's go with radon.
Einsteinium.
Radon is unloved.
United States of America.
Dude, Allie and I tungsten for the win.
Oh, I'm sorry. Hold on. I got these backwards. I just flipped the A and the Z. You can put a set of arrows, you'll be fine. All right. So, A is the atomic number. So, for example, radon has an atomic number of 86. So, radon would be Rn, the atomic symbol, and then its atomic number up top. The Z number is the atomic mass number. Okay, so the atomic mass of radon, if you look up at that periodic table, is 222, approximately. We don't have it exactly dialed in on what the mass is. That's why there's no decimal places. That's why it's in parentheses, stuff like that. All right, because radon has this unfortunate habit of decaying before we can measure anything.
What's its half-life?
I don't know.
Quick, though.
Well, it's not that quick. It sticks around for a while. I honestly don't remember. Ask a chemist.
It has a nasty habit of decaying, but it takes a while to decay.
I think a lot of the isotopes of radon decay very quickly. Some are long-lasting, some are not. So it's hard to get a proportion going. All right. So 86 and 222. And so this would work the same way for anything. Uranium, for the standard version of uranium, that would be 92 over, 235, I believe? 238. Helium you would write as 2 over 2. Actually 2 over 4, I'm sorry. Stuff like that. Okay? All right, to go along with this, we have 3 types of decay. Alpha,
Beta.
beta,
Gamma.
and gamma. Wait a minute.
Why would you listen to me?
No, it's gamma. I just wrote gamma upside down. Okay? Wait, did I? It is Y. I was right the first
I
time.
thought we made it clear that
I was right the
Germany
first time.
discouraged.
I was right the first time. All right, and gamma. It's basically a alpha on its head. All right. So, all right. So alpha, beta, and gamma. Now, I'm just going to someone throw out another element for alpha. Here's your disclaimer. I have no idea if these elements will actually undergo the decay I'm writing out. I am just using it as an example. So, someone throw out an element.
Boron.
Boron. Okay. Boron, which I can almost guarantee doesn't undergo gamma or alpha decay, we're going to make undergo gamma decay or alpha decay, because why the hell not? So, boron. Where is it? Yeah, boron definitely doesn't undergo alpha, but that's fine. All right, so boron. So boron has an atomic number of 5 and atomic mass of 10. Now, the fact that it's got an even number of protons and neutrons tells you it's pretty damn stable, which is part of the reason why boron's never actually going to undergo this emission, but for some reason, we force it anyway.
It's gonna be the goal in life.
Go for it. When boron undergoes alpha decay, remember, the end result of alpha decay is what is emitted out of the nucleus is a helium nucleus. Okay? So it's the nucleus of a helium without those electrons. So what we get is helium 2 over 4. We lose 2 protons, 2 neutrons. There are 4 nucleotides, because that's what this atomic mass number is, how many neutrons and protons total there are in the nucleus. And 2 protons. So this 2 is included in this 4. So there's not a total of 6 things lost. It's still only 4. Just specifying that 2 of them are protons. Does that make sense? Mm-hmm. Fantastic. All right. Plus whatever's left, because conservation of mass and conservation of energy are still in play here. So if we lost 2 protons from the boron, because that's what left in the helium nucleus, that means our resultant atom has to be whatever boron is minus 2 protons, which leaves us with lithium. So notice 2 plus 3 equals 5, 4 plus 6 equals 10. The rows should all add up. Make sense? That's alpha decay. It's a helium nucleus. Remember, alpha decay for the most part, unless you're swallowing it, alpha particles aren't really all that dangerous because they're very, very easy to block. Because anything that'll block helium, like say your skin, will block alpha decay. All right, beta decay. Pick another element.
Argon.
Argon.
All the good chemistry nerds are gone.
Just for that, no, we're not doing argon. Tungsten, fine, tungsten. Again, pretty sure tungsten doesn't undergo beta decay, but it's cool. All right, so tungsten. Now let's say we've got a weird form of tungsten. I'm gonna pick tungsten 184. I'm gonna pick tungsten 184. So that's 73.
Yeah, I got 100% on that.
Now, the reason I'm picking 184 is if you look at its atomic mass, it's got an atomic mass of 183.84, which means its most common form, its most stable form is probably 183, and it's got a couple versions of itself that are a little bit heavier. It's also possible it's a 184, and there's a couple versions that are lighter. My guess is 184 is going to be the less stable version of tungsten.
So where'd you get the 73?
The atomic number of tungsten is 73.
What was 73?
So it is 74. Okay. It's a very, very good thing I have an eye doctor appointment on Wednesday. Because I'm not going to lie, if you're in the back rows, you can get away with murder right now because I can't see crap. All right.
I can see that.
Yeah, because I really give a crap what you do right now. Sit down. All right. Now, beta decay's got a lot of different forms. Yes? Beta decay's got a lot of different forms, so we're not going to go through all of them. But there's electron, or beta plus, beta minus, and electron capture are the three real types of beta decay. We're not really going to get into the details. But with beta decay, and again, this isn't really what happens, but if you think of it this way, it's close enough. With beta decay, think of it as a neutron breaks up into a proton and an electron. Okay? It's essentially what's going on. The real story is more complicated, but essentially you can kind of think of a neutron as a proton and an electron together. It's not like two stick together and you make it a neutron, but you can rearrange the building blocks of a neutron into this stuff. Okay? So you lose an electron. Now, when we lose an electron, we write it like this. Its symbol is the symbol for electron charge and all that other stuff. What do you think the atomic number is of an electron?
1. Negative 1.
Well, the atomic number is 0. It has no protons. The atomic mass number is -1. Because you didn't change your protons, but you did lose a neutron. Or, I'm sorry, you didn't lose a proton, but you did change or lose a neutron. So,
Yeah. Why would that still be 74?
hold on. Hold on. Okay. So here's where I lied. With beta decay, the atomic number doesn't always have to add up.
Oh.
Doesn't always have to add up. The atomic mass number must always add up, but this one can change. It shouldn't during alpha. It absolutely should not during alpha, but during beta decay it will. Because here's the deal. You lost a neutron, right? Wait, hold on. I'm sorry. No, I lied again. No, whoever tried correcting me the first time was absolutely right.
Bootstrap built your liar, and you will spend it.
So you need a mountain.
-1 over here. I knew it.
Okay, I did have the -1 in the wrong place. Because your atomic number is changing, your atomic mass is not changing. What is going on here?
We're too loud.
Let's go.
Your atomic number is changing, yes. Your atomic mass is not changing. Because you're just essentially exchanging a neutron for a proton. I'm sorry. We're back. Let me get my unleaded caffeine going. Hold on.
Unleaded.
For the next one,
What?
It's just Coke. It's not caffeine. Oh,
let's
no.
do yttrium.
Let's do gallium.
There's lead and
Yttrium.
Gallium.
I like it. No, we already picked yttrium.
CF, whatever that is.
We already picked yttrium. God, what atomic number is yttrium
I
even?
don't know.
Someone just asked if yttrium was Jewish? Yttrium is atomic number 39. Yiddish.
Oh. I just thought of the illustration for the AT shirts. Yttrium, like just the bottom.
Yttrium
with the curls and the hat.
Oh God, what is the name of that? Yarmulke. There we go.
I don't think yarmulke is the right. Yeah, it is.
Yeah, it is.
Like that.
All right, yttrium. Let's go with it. Yttrium is atomic number 39.
This is still beta decay, right?
This is gamma now. This is gamma.
What was the quote by Jesus?
Oh,
And let's go with 89.
Yeah, no one will ever understand, including us in 10 years.
Yeah, 10 years ago, I watched this video and just, what was wrong with you? More importantly, what was wrong with that guy? All right, here's the thing with gamma decay. The equation for it is really, really simple. A what?
An asterisk?
An asterisk?
Yes.
Okay, here's the deal. With gamma decay, the atom doesn't actually change. It just simply rearranges itself from a higher energy level to a lower energy level. So what we also have to include is, and I want to double check what the symbol for a photon is. Okay, yeah. So we went from a higher energy level to a lower energy level. So if our energy level is changing, then that means we had to also give off energy in the form of a gamma particle or a gamma ray. So our atom itself doesn't change, it's simply less energetic and has given off its energy in the form of light. In this case, a very high frequency, low wavelength form of electromagnetic radiation. That's gamma. Okay? Now, with beta, this isn't the whole story. There is something else that that I am not including. You should know it, but you don't have to be able to use it for the AP test. There's something else with beta that we haven't included. With beta decay, there is also something called a neutrino. A neutrino we've talked about is something that interacts with mass very, very weakly, but it does have mass.
Is that like a V?
Yeah, it's a kind of weird looking V.
I was about to ask you, it's supposed to be.
It's a stylized V. We'll go with
Are
that.
they like super fast, tiny radioactive particles?
Are they really tiny what?
Neutrinos.
Yeah. They're not tiny. They just interact with mass very weakly.
Aren't they? You can't capture them.
They're very hard to detect. Okay? Trillions a second are pouring out of the sun and impacting the Earth, but we detect maybe 12 a year using massive neutrino detectors. They're very, very uncommon. They're very difficult to detect just because they very rarely actually interact with anything. Billions of them are passing through you every second. You never notice. Let's put it that way.
That's metal.
Neutrinos. Okay? Now here's the thing. The reason I'm bringing this up, because you don't have to necessarily get into what a neutrino is or anything like that. The reason I'm bringing this up is I mentioned there were a couple different types. The other version of beta decay has the same result, except instead of a neutrino, that's specifically an antineutrino, instead of an electron and an antineutrino, it's a neutrino and a positron. A positron being the antimatter version of an electron.
What is that?
It happens all the time, but we're not going to get into the why. Okay, that's a story for after the AP test, if we want to have that conversation. All you have to know for now, guys. Guys, here's your summary for atomic physics. If you see helium atom, alpha decay. If you see electron or positron, beta decay. If you don't see any change in the atom whatsoever, that's gamma decay. If you don't see any physical change in the atom.
Positron just a P?
Yeah.
Okay.
Questions?
So wait, what'd you say for beta again?
What about it?
What'd you say for it again? Helium for alpha and then what?
Electron or positrons for beta. Okay?
Are you gonna have all these columns you have to like decay?
Huh?
How are we gonna use this?
I'm gonna show you right now. Questions? Fantastic. Let's look at some examples then. Once I figure out where I put those examples.
Kevin, would you like a sandwich? Yeah, I would always like a sandwich. It's spicy my favorite. Thanks.
I love that. How about you? I love that.
Joe, you want to split it? Whatever. Because I ate like before I came here, so I'm not really hungry. I ate for the breakfast.
Radon actually is a perfect example of that. And radon is what's in your smoke detector. You guys remember we talked about since alpha particles are so easily blocked?
What's the most like average like that we see every day?
Those average thing you guys see every day.
Like what is things decay? So is this like the same thing as like animal or something that's like slowly decaying?
No, it's different. What we mean by, so what you're talking about is biological decay, where you're turning certain proteins into other groups of proteins. It's all random. Okay, it's all just random chance whether or not this happens or not. Every atom, so if you're asking the most common type of decay we deal with every day, I would say it's probably carbon-14. I'm probably wrong, but off the top of my head I'd go with that. Because inside your body is a certain amount of carbon-14. Okay? Can't avoid it. It's an unstable version of carbon. Every living thing has it. It's what's responsible for radiocarbon dating. Okay? So carbon-14 is always going to decay in your body into, I believe it goes through alpha decay into, I don't know. It might be alpha, it might be beta. It's one of the two. But that would be what I'd say is the most common form. At least that you're going to be going through every day. But you're going to go through a little bit of everything. So it turns out there are a ton of unstable compounds in your body. That's just life. Okay? All right, so let's take a look at this. So we're going to start off. I want to just do a couple of multiple choice questions together. We'll talk about them. And then I want to give you guys a little bit of time to start going through, looking on your own. If you see one you don't get, skip it, then we'll come back and we'll ask about it. But I want to at least get a little practice first. So number one, an atomic mass unit is approximately equal to the mass of a... What do you guys think? Raise your hand for A. This is B. C? D? And E. Beautiful, D. Okay, here's why. Here's why. So remember, when you're dealing with atomic mass numbers, remember how I said that mass number is essentially the number of neutrons and protons? Because neutrons and protons are essentially the same mass. You guys are really loud.
I apologize.
Protons and neutrons are essentially the same. Electrons are essentially ignored in atomic masses for two reasons. Number one, it's not always reliable on how many electrons you've got on an atom at any given time, because electrons you can ditch them, you can pick them up, they're easy. But number two, the mass of an electron is on order of 10 to the negative 31st. The mass of a proton and neutron is on order of 10 to the negative 27th. They're 1,000 times more massive than electrons are. So you're just always going to have more mass concentrated in that nucleus, so you can just pretty much ignore the electrons. Okay, even for the ones with tons of electrons, all of the electrons combined aren't even going to come close to one proton, so who cares? All right, 2. Radioactive oxygen, 15-8. Nucleus emits a positron and becomes. So if it emits
Same thing as an E, where it's negative 1 above it? Or is it...
Yes.
Okay.
Yeah, so if it's positron, what kind of decay are we talking about?
Gamma. Oh, no, wait. Beta.
If we're talking about positron or electrons, it's beta. So,
Are we going to need like a periodic table?
no, you better not, because you're not going to get one. Okay? So, What is 15.8 going to turn into?
What if, like, if we wrote it like that, would it be 8 over 13?
Yeah, I don't know why it's written this way. It's kind of weird. So if it's 15 over 8 and it undergoes beta decay, what would happen?
It'll become 10. No, when it's an electron, the number goes up. If it's a proton, the number's going to go down. So it's A.
So.
Okay, yeah, I suppose I should have mentioned that.
16.
Okay.
Wait, what?
Yeah, hold on. I'm realizing my mistake. I kind of assumed something, and that was my mistake.
I assumed you guys were smart. My bad.
Not what I meant. All right. I said a positron is the antimatter version of an electron, right? Okay, so what I assumed in there was what went without saying, and I shouldn't have because it's not intuitive. It does the opposite of the electron. So when you emit an electron, the atomic number goes up by 1. When you emit a positron, it goes down by 1 because it's the opposite. My mistake.
Yeah, so it's
My mistake.
That's easy though, because
No,
like
like-
electron is negative. and
Yes.
positron is just
Yes.
positive.
Yeah. Okay, so with that knowledge now in hand, so instead of this being -1, it should be +1. So with that knowledge now in hand, what do you think?
Wasabi.
Because if you look on the,
Oh,
if you
yeah.
look at above it,
Is it-
Hold on.
I mean, you shouldn't necessarily need the,
And then this is external.
You know what? Let's skip 2 for now.
it should be 8.
No, it shouldn't.
No, it's, what is the problem? Is 8 over 15?
I mean,
The reactions inside one body. And
Wait, hold on.
look at, yes,
Okay, no, I'm getting the weird way they're writing down this crap now.
yeah.
Should be 15 over 8, it should be 8 over 15.
What the deuce?
Let's just skip 2 just because they wrote it really weird.
Yeah, but if you were to switch your own.
Yeah, no, you're correct. It should be 8.
Yes.
Should be 8.
I know.
All
You
right,
just
but
wrote it
let's.
weird.
No, I'm sorry. It should be B.
What?
Should be B because your atomic mass number cannot change.
Oh, yeah, you're right.
Right. But again, let's just skip 2 because the way they wrote that is really kind of funky and is making me uncomfortable. All right. What's up?
So it's one.
Oh, they.
write all of them like that.
That's irritating. Apparently, that's the old way they used to write it because they don't write it like that anymore. All right, whatever. We'll just go with it. So. Oh, I know what happened. No. It's not how they wrote it. It's how Word formatted it. It's how Word formatted it. Because to print this off, I had to save it as a PDF because the Word document wouldn't print for some reason. And then the conversion, I think it got screwed up.
No.
Okay.
Wait.
So I'll write what it should be. Okay. So for number 3, a radon nucleus, radon which should be written as
6 over 2.
emits an alpha particle. So, if the formatting is confusing you because it's weird, just go ahead and write down on a piece of paper. What do you think the number should be?
Yeah.
What's 3?
Oh, this is 4.
Now, the atomic symbol is PO, but I was asked before, do we need an atomic periodic table? No, because you don't have to know the symbol, because they are not going to lie to you. They're not going to present to you 2 different options that have the correct atomic numbers, but they mess up the symbols, because they're not looking to know if you memorize the periodic table or not.
Awesome.
So all you have to be able to do is recognize, I should see the numbers 84 and 216. The only option there is polonium, which is option A.
From Shakespeare.
Number 4, when it says that it makes beats, that should be beta.
Yeah, that's beta minus. So that's just normal beta decay.
So E?
That's an electron, yeah.
Okay.
Alright, so tell you what. Try skip 5. Skip 5.
What about 4?
Well, I'm just going through and making sure there's none that you guys haven't had a chance. So skip 5 and then try the next couple. Other than 5, pick some random ones. Try them. Try them with whoever's sitting next to you. Try them by yourself. And then we'll just kind of crank through some of these. So let me pause the recording real quick. So what is it you want?
Just write down like what an electron is, positron, or neutron.
Okay, I can do that.
To be
The way the
double.
numbers are.
Okay, yeah, that I do apologize for. I'll try to make up a version that fixes that, and I'll throw that up on Moodle. You stop that. All right. So.
Now it's sticking in my head, and I feel like tomorrow you're gonna be like, you did it again. But I don't, you don't want to tell me.
Okay. So a proton would be 1-1. It's got one proton. That's one atomic mass unit. A proton would be the positive charge in a nucleus. Then you've got a neutron. That one's 0-1. Generally, we actually use an N as the symbol for neutron.
So we use for
Usually we don't really, I don't know exactly what we use. I would say a P, but that's generally what we use for positron. Generally you don't do much with protons because you usually don't have just protons flying around. Okay? Neutrons, again, you can imagine them as an electron and proton combined. Not exactly what it is, but close enough. Okay? Then you've got electrons.
Nicole's unraveling.
What the heck does that say?
It's supposed to be electron.
Election.
Why don't I just erase that one and try again? Yeah, that's starting to look like things it shouldn't look like.
Yeah. We don't do politics in here. We can't have the word election up there.
All right. So electrons, again, we should be completely familiar with what electrons are at this point. Then you've got positrons.
Puzzlesons, it looks like.
There we go. Positrons. Positrons are the antimatter version of electrons. So essentially you can treat them as exactly the opposite of an electron with the exact same mass.
Okay.
Okay? Opposite charge, opposite effect on an atom, blah, 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 blah. Okay? Alpha particle. It's going to be a helium nucleus. Beta particle is either going to be electron or positron, and then gamma particle is just energy. That should pretty much be everything. We don't really use deuterons, and I mean, let's put it this way, I've never heard of them, so they can't be that common.
Deuterons.
Do you tron?
Number 10.
Do we?
Right. So guys, ready to go back over the questions?
Of course.
Of course.
Really? No.
Huh?
Calculator, yeah, it's gone.
I mean, you can borrow a calculator.
No, I mean, I'll give you $50.
No. Would you like to borrow a calculator for now, though?
Yeah.
Okay.
It's empty. Your reflexes are so bad.
All right.
Push this whole thing.
Guys. of here soon, I promise. All right. Yeah, we have. All right, so where were we at? 7?
Time flies when
8 is A, 9 is A. B, 10 and 11 are B. 12 is B. 13 would be E. Yeah, E like eh.
What was 10
10 and 11 are both B.
Oh, is it because all the
Do you want all the answers really quick? Just so you have them to study for later?
Are you going to be online?
Well, okay, let me put it this way. Here's what I'm going to do. So I think I've shown you this before, but I've got these workbooks that I got from another teacher that is like, at least like 40 multiple choice and like 20 or 30 free response questions for every single topic, including the worked out answers. So here's what I'm going to do. My project this week is I'm going to put a copy of all of these files up on a Google Drive folder that I will give you guys all access to. So my goal is that all of these will be online so you can go look stuff up yourselves, find the practice problems yourselves, all that kind of fun stuff. But I can run through the answers now if you want them because this is probably not going to happen until the end of the week. So let's just run through them now, I guess, real quick. What's up, Carson?
Do we need to know vision?
Yes, you should know the difference. And I'll bring up one more thing about that here in a second. Yeah. Yeah, that's not a big deal. Here. Go use the faculty ones. They're really crappy. Don't worry about it. They're nothing exciting. Except someone went and put motivational things all the way in the faculty classroom. It's kind of disturbing. All right.
You can do it.
Not quite. Not quite. Shh, guys, come on. Bring it back. All right. So remember, fission is when two atoms split. That's going to be anything bigger than iron. Fusion is when two atoms combine. That's going to be anything smaller than iron. Okay, but remember, iron is that break point, and that's why iron kills stars. Remember we talked about all that? Okay, that's that break point for what's called binding energy. All right. So, continuing to run through, where did I leave off? 13?
No, 14.
All right. So let's see. 14 is 14 is E. 15 is E. 16 is D. Impressive. 17 is A. 18 is E. 19 is B. 20 and 21 are A and E. 22 is C. 23 is E. 24 would be D.
you say D or B?
D, delta.
As in doggy.
As in, yeah, sure. 25 would be A. 26 would be E. 27 is A. And 28 is E.
How do you mean the angle for 28? Like, what do you mean by like the angle between the mass and the emerging protons?
Okay. Let's talk about this real quick. So, excellent question. This kind of gets into what I was going to talk about with the free response on the back. I guess. So, the question is for 28. So, the question is we got an electron and a positron. They each have the same mass. They are all in the general vicinity and have very small initial speeds. They annihilate each other in producing two photons. And so then the question is, what is the emerging pass of the two photons? Guys, here's the deal. Conservation of momentum still applies to atoms. So if they have very tiny speeds, but if they have mass, that means they've got a lot of energy, right? So those photons are going to come out fast, but they have to come out in such a way that they're, if they say they have very tiny speeds, that means there's very little momentum, yes?
Yes.
So the reason you know the answer has to be 180 degrees is for them to cancel out and have a net momentum of 0, they have to go in opposite directions. That's it. It's conservation of momentum. So if they essentially had 0 momentum before, they have to have 0 momentum after. So you treat it like an explosion, which is literally what that would be. So 0 momentum before means 0 momentum after, which means equal momentums in opposite directions. Make sense?
Yeah.
Beautiful. Any other multiple choice you'd like to explain before we take about 10 minutes on the free response?
How do you do photons?
Pick one. Which
I
problem?
was gonna say, like, when 27, how would you do that, like, without a calculator?
Magic.
Oh, I just realized it was perfect.
Kayla, you okay?
Oh God.
It doesn't have to in my head.
How do you do that in your head?
Did you see my story? Look at my story.
You don't.
Come on. You put me on your story. Look at my story.
Okay.
Here's about what I would do. Here's about what I would do. Okay. You know it's about equals MC squared, right?
Yeah.
Okay. Look. So here's what I would try and do. I would try and say, all right. So according to this problem, we've got equals MC squared. All right. C is in the neighborhood of times 10 to the 8th, right? All right. And so times 10 to the 8th times 10 to the 8th, what's that going to give you? Well, so, okay, here's just your handy little tip. If you've got two numbers with scientific notation and you are multiplying them together, you add together their exponents. So times 10 to the 8th squared is times 10 to the 16th. Because it's times 10 to the 8th plus times 10 to the 8th. To the 8th plus to the 8th gives you plus to the 16th. Okay? So this c squared works out to be about 10 to the 16th. We know the mass is 9 times 10 to the negative 31st. Was the faculty bathroom everything you hoped it could be?
It's very inspirational.
They like have a soundtrack in there from a Karate Kid.
They're watching
Okay, so
little pictures everywhere. They had like inspirational quotes on them.
you know the one that bothers me is the little thoughtful velociraptor that says, "If I slap you with a dictionary, is it oral or verbal assault?" Because it's neither. Because words in a dictionary are not verbal. Whoever put that up is an idiot, and it bothers
I
me.
didn't see that
A
one.
philosopher.
All right. Yes. So no, I'm dead serious. That's not
That's
what.
not motivation.
Someone looked at the back
All right.
popped open.
The one that does it is they have a silhouette of a guy, and it says, "I see a little silhouette of a man," and then underneath it says, "If I'm correct, you just sang this." Anyway.
I only sent them memes.
So here's the deal. Again, we've got this situation right here. We got this situation right here. Where we've got 10 to the negative 31st and 10 to the 16th. So you can kind of mentally really quick go, okay, well, negative 31 plus 16 gives you...
No, it's a negative. Right?
Negative 15. Okay? Now, really quick, because when you multiply when you're multiplying scientific numbers, you just add their exponents together. Okay? Times 10 to the 9th plus times 10 to the 6th will give you 10 to the 15th. Okay? Are you recording this? No. Kind of weird. A little creepy, dude. All right. So 10 to the negative 15th. Now, then we do have numbers in front, right? So we've got 9 to the first, and then we've got, this is 3 times 3, so that's going to be 6. 6 times 9. You know what? Let's subtract one more exponent from here. Because
What?
you've got a 9 in front of this number, right? You've got a 6 times 6 over here.
Where did you get that from?
Where did you get that?
Because the mass is 9.1 times 10 to the negative 31st.
Oh.
3 times 10 to the 8th.
Okay.
So what I'm saying is when you multiply all those exponents together, you're going to get something around 20. So let's knock another 2 off of this.
Oh. Multiply 9, right?
Well, it'd be 9.1 times 3 times 3. Right? Because 3 squared.
But then wouldn't you have to multiply it again?
No, because each particle is going to produce 1 photon. So you're only dealing with that once.
Okay.
All right, so what I'm saying is estimating this is going to be around 10 to the negative 13th. And then it says electron volts. Well, to get electron volts, you divide by the charge of an electron, which is 1.6 times 10 to the negative 19th. So then this is going to change from negative 13 to positive 6. And so you're in the neighborhood. Okay, that's how you estimate scientific notation. You ready for your real answer? Skip this and do it at the end. This multiple choice question is a perfect example of what you should skip and come back to. Chances are I would not do this problem in my head. So, for now, for problems like this, if you use your calculator on it, great, do it. Because then at least you know how to do these problems. And then if the problem is when you come to the AP test, you just can't do the math in your head, guess what? 90% of the country can't either. Don't worry about it. That's a problem a lot of people are going to buy.
As Mr. Womack would
And those 5% that can do it, they were getting 5s anyway. All right, what else? All right, ready to talk about the free response?
Yeah.
I'll take that as yes. All right. So flip to the back. All right. So I want to do number 1. We got a lithium nucleus. We're at rest. It decays into helium. Decays into helium. And a proton, we have the rest mass of both of them, as shown by the following reaction. All right. In this reaction, momentum and total energy are conserved, as they should be. After the decay, the proton moves at the speed of 1.95 times 10 to the 7th meters per second. A, determine the kinetic energy of the photon. What does it sound like you're going to do here? Kinetic energy. And that's part of the reason we didn't do a whole lot with the free response. 90% of the free response that involves atomic physics is just doing normal mechanics with big numbers. That's it. Who's being a parrot over there? It was the hopes and dreams of fairies. Yeah, I think we're going to be done here soon, because I think everyone's starting to lose it. I think everyone is absolutely starting to lose it. You take naps?
I don't, but I didn't say.
Naps are good for your heart.
I'm actually
I accidentally took a 5-hour nap.
Hey guys?
Is that 195 or one dot?
Yeah, I agree. I'm kind of...
Yeah, that is supposed to be a
With
dot.
scientific notation, it has to be.
No, it doesn't.
Well, they told us
It should be, but I never do it.
that either of those
You have to have more study sessions.
doesn't kind of.
Yeah, I just got lazy. Alright. Guess?
Doesn't got lazy imply that she would not lazy.
Yeah, no kidding. B. Determine the speed of the helium nucleus. What do you think we do here?
I have to determine the speed of the helium nucleus. Give me a second. Open my brain.
Because this is why math teachers don't like me, okay? Leave me alone.
Oh.
I'm inconsistent at best. Yeah.
Well, We know the speed of the proton. Oh wait, hold on.
We know the speed of the proton.
Wait, hold on. Did I miss something? What is it? Never mind.
So guys, they give you a huge hint. Now, I'm not doing the math along the way, because I figure you guys can type stuff into your calculator and be perfectly fine. I just want to talk about kind of the gist. All right. They tell you both momentum and energy are conserved. Well, what do they tell you about the lithium nucleus before the decay?
At rest.
It's at rest. So what does that tell you about the momentum of the lithium nucleus before the decay? It's 0. So what that means is the momentum afterwards, we have two objects after, we have 0 before. So the momentum of the photon must equal the momentum of the helium nucleus. We know the mass of the photon, we know the mass of the helium nucleus. We know the velocity of the photon, we can find the velocity of the proton. I keep saying photon with mass, and that's not right. Proton. So we know the masses, we know the velocity of the proton, we can figure out the velocity of the helium nucleus by setting mv equals mv. Make sense? C. Determine the kinetic energy of the helium nucleus. Well, if you know its velocity and you know its mass, can we calculate the kinetic energy?
Yeah.
Determine the mass that is transformed into kinetic energy in this decay. All right. This is the one I want to talk about. All right. So here's the deal. I don't know why I'm pulling this up for numbers. Okay, so for A, you should have gotten 3.18 times 10 to the negative 13th. B, you're going to get 4.91 times 10 to the 6th. All right, so, and then C, you should get 8 times 10 to the negative 14th. Do you want me to repeat those again so you can write them down? Yes? Okay. So for A, and then I'll, once I answer these, I'll get to you, Carson. A should be 3.18 times 10 to the negative 13th. B should be 4.91 times 10 to the 6th. C should be 8 times 10 to the negative 14th. Okay. Questions on any of that? All right. So this is where we get into mass deficit. For part D, I'm sorry, I said I'd get to you, Carson. I almost forgot. What's up?
So on the AP test, you don't include units. Will you get marked down for that?
Maybe. That one's a tough one to answer because, like I've said before, they don't go into the test knowing what each question is going to be worth. Well, they know it's worth 15 points, but they don't know how those 15 points are broken down. So if you look at old answer keys, which we've looked at several of, pretty much what you'll see is the only time they include units is if there's like 1 point at the end of the problem that says 1 point for all included units, or for including all units. Units are a point they kind of use as a, I don't know what else to give you. So generally, if you don't include units, you're not going to get killed for it. I still suggest doing it because that's an easy point to get, and it makes it clear to the grader your thought process. So if you include units along the way, you're more likely to get partial credit. But it's not like chemistry where if you don't include units, you're not going to get past a 3 or anything like that. Chemistry, they are very anal retentive about sig figs and units. Physics, not so much.
Is it?
We're anal retentive about units, just not on the AP test.
Was it possible to get like half points?
No. Half points don't exist. It's just too hard to objectively give half points. It's easier to round to the full point in terms of consistency of grading. All right, any other questions before we move on? All right. So D asks, determine the mass that is transformed into kinetic energy in this decay. So here's the thing. What do we know about... What's the kinetic energy of this nucleus before the decay?
0.
Why? Because it's at rest. There's 0 kinetic energy before. What's the kinetic energy of the photon after the decay?
Proton.
Or the proton, yes, I'm sorry.
3.18 times 10 to the negative 13.
Okay, what is the kinetic energy of the helium nucleus after the decay?
Oh, 8
Whoever.
times 10 to the negative 14.
What?
8 times 10 to the negative 14.
Okay. So here's the deal. If we had zero kinetic energy before, and we have this kinetic energy after, well, what's the sum total of that going to be? Really quick, wouldn't that be like 4.98 times 10 to the negative 13th? Someone double check me with the calculator.
Did you add it?
I think so.
Multiply.
Yeah, you want to add. Sorry. See if I did my unit conversion right.
3.98 times 3.
Yeah, 3.98. Where'd the 4 come from? Okay, so this is just the sum of these energies. We had 0 before. Now we've got this much energy. Well, where did that have to come from? It had to come from mass lost from the lithium ion, or the lithium atom. The lithium atom had a certain amount of mass. Afterwards, there's less mass, but more energy. Well, where do you think you plug that into? What's our only equation for atomic physics?
E equals mc squared.
E equals mc squared. There's your energy. You're looking for the mass. The speed of light's a constant. Plug it in.
Is it safe to say that for these problems, like the free response, is it safe to say like if you put E equals mc squared in the problem somewhere, like if you're asked in nuclear physics, like you're guaranteed at least
A point? Sure.
some point?
Generally, yes. Generally, by at least including the right equation, you're going to get a point. Yeah. Okay. And then the last part for E says, what's the rest mass of the lithium ion? Or the lithium atom? Well, guys, they tell you the mass of the proton. They tell you the mass of the helium atom. And you just figured out the mass that had to have been lost to energy. If you add those three up, that had to be the mass of the lithium ion.
What is the speed of light again?
3 times 10 to the 8th. Yep. All right. I don't know about you guys, but it's getting late.
I don't know about you guys, but if you have a range.
No.
Can you try this to us?
What?
Keeping this out?
Well, here's what I'm just saying. Pretty much at this point, well, I am stopping this.